Boom. Hello and welcome back to Precalculus1. You voted to have the exam, so here we go again with the review. So exam 3 is on chapter 3. And I am going to sneak one problem in. I am. And that's going to be that long problem that took a whole page where you use the synthetic division and all. Yes. So plus the PERS factoring, long problem. So you have to figure out the list of possible rational zeros, that's the PERS, and then the Descartes rule of signs, and then do the whole thing with synthetic division and so on, and then finally part D, write the factors like x plus 2, x minus 1, x plus 7, whatever they are. I was not happy in how that problem went on exam 2 in general, and that's the central and the most important problem of chapter 2. Polynomials are very nasty in terms of finding roots. And that's the problem that finds roots. Everything else later on in calculus, with polynomials, you can't wait to have a polynomial around. Except when you have to find roots. It becomes a nightmare. Everything else, calculus not so pleasant with it, but you can find roots. So yeah. So chapter 3 has only 5 sections. Now, I should have just 5, right, bullet points, but I'm going to have more bullet points than that. So, we already said there is PERS, right, from chapter 2. And then we have exponential function. Now, exponential function is going to be, so let's use pluses here and then little minuses over there. So knowing that y equals b to the x, right? I'll put specs. What do I mean specs? Well, those are all the intercept, asymptotes, domain, range, all of that stuff. So domain, range, intercepts, asymptotes, so specs on it. Graphing. Guess what is not, what is going to the non-graphing calculator part? Exactly, graphing. So shift left, right, reflect. So the whole 1.6 deal applied to this. This is your 3.1. And now, log function, same stuff. Y equals log base b of x. Specs. Graphing. Then we have log rules and log properties, log formulas, all of that good stuff. Oh, come on. Now, under log formulas, we have conversion, we have calculations, we have change of base. Oh, actually, no, that's here. We have the expand, compress, the power rule, right? All that stuff under log formulas. Then we have exponential and log equations. We are talking about obviously 3.4. This is 3.3. This is 3.2. That's 3.1. There we go, much better. So exponential / log equations. And for these, we must know conversion as the basic, kind of always works thing. But also comparison. Comparison is a very powerful way of solving problems. And then we have ln or e on both sides, which is also a powerful way to solve equations. And I'll do examples of that. And then we have finally word problems. Something that you all waited for, 3.5, where we are talking about y equals a e to the kt, k larger than 0 growth, k less than 0 decay. What happens if k is equal to 0? Neutral. There's no growth, there's no decay. K equal to 0 makes exponent 0. E to the 0 is 1. So whatever the initial stuff is times 1 is the initial stuff. It's status quo. Alright, so what else do I have? We have decay problems with the half-life. Well, so growth. Let's go growth first. Growth. Like population. Or money. You are going to memorize A equals P1 plus R over N to the NT for money. And we have decay, which is radioactive, garbage, drugs, and all that kind of stuff, where you are introducing a very important concept, lambda, half-life, which occurs when you take the original mass and cut it in time in half as a point. Two-step problem. So the exam is going to take, the standard time of hour 20. 10 problems, again, 2 parts. Some of you who took forever last time to solve first 4 problems and then rushing to the second 8, hopefully you're not going to make the same mistake. And also the final is going to be the same way, the 2-part final with the thing. So you have to practice this skill of, switching. I will give you the suggested time to switch, which you are welcome to ignore. I know. It will be on the board. So the clock is right there and it's apparently working. It's a little bit ahead, but that's okay. We'll go by that clock. So you can all switch in appropriate time. Everything else is the same. You need scientific calculator at least. You can bring the graphing one as well. Your calculator will be used only on the calculator part. We will start with a non-calculator first. Testing center exams, the same thing. So non-calculator first, and then as soon as possible switch for the other. Generally, if the whole exam is 12 questions, because some are like this, 4 and 8, you should allocate 2/3 of your time for the, 2/3 of the time for the longer part and 1/3, right? If you have 4 and 8, that's 12 problems divided into, right, these thirds. So try to finish the first one in, like, let's say 20-25 minutes, the first part. Testing center, obviously 30-35, maybe 40 pushing, but not so much. And then the rest of the time for the rest of the exam. And the non-calculator part means no calculator of any kind. Now, non-calculator part will have problems to compute logs and exponentials without a calculator. We covered those problems in class. So, if I ask you what is log base 3 of 1 over 81, that question is on a non-calculator part. And that is no calculator of any kind. Not no graphing calculator, but no solar calculator, no scientific calculator. So, solving this, you might say, all right, so this is log base 3 of 3 to the negative 4, because 81 can be written as 3 to the 4, because it was in the denominator, bump it up. And now you know that 3 and 3 are the same base, so negative 4 goes in front. You have log 3 of 3, which is 1, and you get the answer of negative 4. So all of the answers on the non-calculator part that have these kind of calculations should work out to be what you call a nice number, because you like to discriminate and you're awful people. You see a decimal, oh, that's a bad number. Or see a fraction, that's an awful number. No, it's just you're awful. Don't discriminate, it's not nice. Fraction is a number just like everything else. Anyway, you're looking for the whole number answers, most likely, right, for this part. And you will be exploiting this fact that log A of A is 1, right? ln of E is 1, because we know that ln is a lazy notation for log base C, and then, right, using the same thing. Also known fact that A, log A of X is X, right? So all these inverse relations, because exponential functions and logarithmic functions are inverses of each other. So these are the types of things that you will exploit on the non-calculator part of the exam to compute things. So 2 raised to the log base 2 of 7 is just 7, because log and 2 and to the exponent, they cancel out. Now, I know that you all know this because this was clearly on your lab and you all completed your lab. So you all know these calculations, so there's no reason for me to talk about this at all. I'm sorry for wasting your time now. It's the third time you dropped it. Check it works. See, I told you it's going to be useful. So non-calculator part of the exam contains graphing, and it contains these calculations. Now going to graphing. Y equals 2 times e to the x plus 5. Well, you start by drawing the dashed e to the x, which is your default state. And now what is this plus 5 going to do? Very good. So plus 5 is 5 to the left. So this point here is going to go 1, 2, 3, 4, 5. So it's going to look like this. And as you can see, instead of kind of sluggishly going up over here, kind of sluggishly going up, we're going to go up faster because it's times 2. This times 2 makes it turn faster rather than default one that looked like that. So this is 1 times and this is 2 times. It goes faster up. That should also make more sense, because if this is the twice amount of, right, twice as fast to get money, right, the graph is going to turn up faster, right? So in shorter time, you make more money. And label x and a y, obviously, for full credit. The evil case is when you have 3 raised to the, let's say, negative x plus 2. Now, why is this an evil case? Do you remember this a month ago? Yes? It is reflection, but what we have to do before we hit the reflection, there's something that I told you must do, otherwise you're doomed. Is this left or right? What? It's already distributed. It's the other. See? See? Yeah. You have to go right. And now you go, it's plus 2. No, it's not plus 2, it's minus 2. It's minus 2. Boom. So, the minus is going to do reflection as you suggested, but then you see that negative 2, it's shift to the right. So, we start our good old graph, right? Drawing the default case, that's 3 to the x. And then reflection on what axis? X or y? Y, nice. It's going to look like this. Going through, again, through 1. And then what do you have to do? Right 2. Beautiful. So what used to be at 1, it's going to go now 2 units to the right. And we keep the same shape of the graph. There it is. So y, x. And you label this point as 2, 1 for full credit. I mean, if you don't want full credit, don't worry about it. So from 3 to the x, default state, reflections are done first. You know you're 1.6, you know you're supposed to do reflections first, and then shift up, down. And then the stretches and shrinks, they're not humanly possible to do, you know, the greatest job at those, but you do your best. Log graphs, same. Log base 5 of x minus 2. What is this minus 2 doing? go to the right. Yep. So log goes through 1, original state, and now we have to go 2 units. So your good old vertical asymptote that was at 0 is now going to be at 2. The point at 1 is now going to move to the point at 3, because everything shifts 2 units to the right because of the -2. Let's take a look at the question, log base 5 of x minus 2. What now? Yes? Beautiful. So these parentheses, right, are not for decoration. If you have parentheses, shift to the right. No parentheses, shift down. Why? Well, remember where the logs belong in PEMDAS. Log is the operation that is applied to x. And in PEMDAS, the logs and square roots are on the same level as exponential calculations. So you have to apply to the x log first, and then 2, which is the reason why this 2 is hanging out by itself, and it's a shift down. Where if you have this way, you have to do subtraction first, which is shift left and right, and then apply log, because parentheses are still ahead of logs and exponents. So it matters where you put whether you put parentheses or not. So this is going to be a standard log going through 1. This is log 5 of x, and then you are going to shift that log from this 1 2 units down and draw the same log, and call this point here 1 and -2. All good? Happy? And the next part would be all calculator. Now I also have on a calculator part some problems where calculators will be useless. You can't use a calculator on a problem which says compress or expand, right? No calculations in that case. Calculator is useless. But I didn't want to cram the other part, right, of the test. So I can say expand on a calculator part of the test, and calculator is useless. So expand log base 2 of x squared root y divided by 3z w to the 8. Let's see. Actually, let's do 2z. There we go. I just made this up. So expand this. Try to remember this stuff from 2 weeks ago. Maybe even more. No, 2 weeks ago. So we have log base 2 of x squared plus log base 2 of root y minus log base 2 of 2 minus log base 2 of z minus log base 2 of w to the 8th equal to 2 log base 2 of x, the exponent drops in front, plus 1/2 log base 2 of y, the exponent, which was 1/2, jumps in front, minus 1. Log 2 of 2 is 1. Minus log base 2 of z, and minus 8 log base 2 of w. That's the expansion. Now, equations. We talked about simple cases where we have 3 to the x plus 2 is equal to 1 over 9. Now that would be a simple case because you can do it by comparison. In many cases you can't use the comparison. In this one we can. We have a common base of 3. Right? You can write 1 over 9 as 1 over 3 squared, and you can bring 3 squared up, changing the sign on the exponent. This is all your basic algebra from last semester. And now you use the comparison, not the conversion, use the comparison to say that x plus 2 is equal to negative 2. Subtract 2 on both sides to get x equals negative 4. Now if you plug negative 4 back in original problem to check, you get 3 to the negative 4 plus 2, which is 3 to the negative 2, which is 1 over 3 squared, which is 9. 1 over 9. So problems like this are solved by comparison. Here's another example. Log x plus log x minus 1 is equal to log of whatever, 5. So you know that you are supposed to compress these into a single log. By the way, what's the base over here? Base is 10. So when we're solving equations, we compress everything into a single log. And now, since we have log on both sides with the same base, we just compare them. So x squared minus x minus 5 equal to 0. And now you have to solve this. Now I picked, the 5 is a bad, right? 5 won't work. So how about 3? Change all these 5s into 3s so we can do it. So to factor this, you get x minus 3 yeah. Change to 2. Oh, you're writing in pen? Good. So it's x minus 2, x plus 1. And then x is 2, and x is negative 1. Now this is very important to check your answers, because some of these answers might actually not be answers. So you plug in 2, and what do you get? So for check, you get log 2 plus log 2 minus 1. It's supposed to be log 2. Well, log 2 minus 1 is log of 1. And log of 1 is what's log of 1? 0. So because this is 0, you have log 2 equal log 2, you're good to go. And now you use the other one. Log negative 1 plus log of 2 minus, no, negative 1 minus 1. Is that equal to log 2? Hell no. This one or this one can't compute in real domain. Can't compute those. Negative number, log of negative number is not defined in the real. It doesn't exist in the real mathematics. If you involve complex numbers, you have answers. But we found that solution of negative 1 is not good. You have to take it off the list because it's what we call an extraneous solution. Solution which you get through the process but do not count. How about 5 times 3 to the x minus 1 is equal to 97. Try this equation. What's the first step? What's the first step? Divide by 5. So we end with 3. X minus 1 is equal to, and now 97 divided by 5. 19.4, right? Now what? Do we have a common base of 3 with 19.4? We don't, right? So we are forced to use conversion. Common sense. You know what the conversion is equivalent to? -2 on both sides. Divide by 5 both sides. That is a standard thing that you do when you're solving equations you learn in algebra. Welcome to log and exponential equations. When you say conversion, that is equivalent of subtract 2 on both sides. So now we are writing log base 3 of 19.4 is equal to x minus 1. Conversion. A to the b equals c converts to log a of c equals b. So now there's a change of base over here. So you go ln 19.4 divided by ln of 3 is equal to x minus 1. All right, so ln 19.4 close parenthesis divided by ln of 3. 2.6991 is equal to x minus 1, and now plus 1 to both sides, x equal to 3.6991. Let's check. Five times 3 to the 3.6991 minus 1 needs to be 97. Well, 5 times 3 to the 2.6991 needs to be 97. So 5 times 3 caret 2.6991 is 96.9992. Well, that's good enough. Because we had to round. See, it's good. Whenever you solve an equation, you plug x back in to make sure it works. Now for your logarithmic equations, it's especially important because you can run into extraneous solutions and then clearly right. What else? Do you have any questions, concerns, anything at all? We talked, oh yeah.
The homework I was doing the other night, and they gave us the thing, the end, but they wanted us to find the half-life.
Okay, that's a cool question. So we know K want to find out lambda. Well, what we know is that mass is equal to initial mass e to the kt, and we know that all of the points are Tm, but if we involve alpha, which is the half-life, we have, sorry, alpha, lambda. Half-life, then the mass, the original mass gets cut in half. So when you plug this in, m's die off, ln both sides, you get ln 0.5 is equal to k lambda. We see that the lambda is equal to ln of 0.5 over k as a formula, and also there is k equals ln 0.5 over lambda as a formula. These formulas are derived from a simple definition of knowing what half-life is. So if one is given, you can compute the other one like this. Always ln 0.5, and you plug whatever, you divide by whatever you have to get the other one. Happy? You don't have to do a dance. Any other questions, concerns? Questions? All right, then I'll see you in 2 days with the exams that are yellow and white and whatever else.